Okay, so Hilbert polynomials. So this is not the most classical version of Hilbert polynomials. There's kind of one step lower than this that we could talk about. It's more basic, but let me just okay. So we're kind of like two levels. We're gonna go. Okay, so let me just start. Okay, and then maybe I'll say what I wanted to say in a second. So D is going to be a divisor on a projective variety. Okay. Okay, and then we can and x. Okay, and then we can look at this function, this Hilbert function. The Hilbert function takes a number t. T is a natural number, and it maps it to the Euler characteristic of this times t times this divisor here. So this is kind of like okay, so in certain cases, this is equal to, so you should think this is equal to h0 of td. Okay, so the higher ones are going to vanish eventually. So like if this were ample, right? So let's put like a little dot here. And so then you could think that this is kind of maybe the global functions where you're going to allow poles here, and then you're kind of increasing t, and you're going to see how this thing grows, okay? Okay, so that's kind of the motivation for the original version. The lower version is kind of like this, and then it's actually for varieties. And but okay, so then we're going to just do it for divisors, and then we're just going to we're going to talk about this theorem in this context and look at it for Euler characteristics. Actually, the growth and decay-Riemann-Roch formula, the quick and dirty proof is that the growth and decay-Riemann-Roch formula tells you that this is going to be a polynomial in T already. We can write down this polynomial, and I'm going to do this in the case of surfaces. But first, let's observe that. So let me just state this theorem, and I guess this is originally due to Hilbert. Is that this function h is actually a polynomial. Is a numerical polynomial. Numerical. So by a numerical polynomial, I mean a polynomial with coefficients in Q such that when I plug in integer values, we're going to get an integer back. Okay, so this is a numerical polynomial, and the definition is that h, which depends on x and d, is called it's a function of t, is the Hilbert polynomial. This is the Hilbert polynomial of D. Okay, so this is kind of the one-dimensional version of Hilbert polynomials. So there's the higher dimensional version, which is what I want to talk about. So the higher dimensional version is the following. It says, so higher dimensional. Okay, or sorry, higher rank, maybe? Higher rank. It's not really higher dimensions, because the dimension's really changing. And then they just put like higher dimensions. Let's put this all in quotes, because I don't really like this name. But I just want to call like maybe a multi-Hilbert polynomial. The idea now is that you take tuples of natural numbers, let's say r of them, so t1 to tr, and we're going to map it to the following. We're going to map it to, we're going to do the same thing, and then we're going to take x, and then we're going to do t1 to d1, and then we're going to do tr to dr, like so. Okay, so we're going to take actually a bunch of divisors on a projective variety x. And we're going to do this function, and the theorem is I don't think this is due to Hilbert, but it's the same thing, right? It's not due to me, certainly. This is an old thing. This is a birational. I actually don't know who did this. Maybe so. Cox studies things like this, and there's rings associated with these things called Cox rings. Then there's okay. So it says that if we call this function h is a multivariate multivariate. So this has multiple variables, numerical polynomial. And the idea that then we say we give a definition. This h is it depends on d1 through dr and on, of course, on x, and it's a polynomial here in r variables, and this is called the maybe the multi-Hilbert polynomial. Hilbert polynomial. Okay, so this is what I wanted to talk about. All right, so I want to talk about the proof. Maybe I can talk about the proof in higher dimensions. Okay, so let's talk about the proof. So the proof uses this thing, what we can call it maybe. So the proof is inductive. So the proof uses two types of induction. So the proof uses two inductions. Two inductions. Okay. So let me just start. Okay. So the first thing that we need to establish is the Hilbert polynomial. So we need to establish the Hilbert polynomial in one variable. Okay, so this is the thing. We're going to induct on the number of variables and then the dimension of the variety. Okay, so this is the number of variables and then the dimension. Okay, so first we're going to do the Hilbert polynomial in one variable, and to do this we're going to do induction on dimension. To do this we're going to use this thing that I'm going to call the positive-negative sequence. Okay, and so what we do is we take our divisor. So we're going to do one variable first, and we write it as the positive. So we have two effective divisors, and we write it as the positive divisor and a negative divisor. Okay, and then we have the following sequence. Okay, so we have the following. We have this sequence here. Maybe I should call it positive-negative sequences. Okay, so and then we fix an integer m, and then we have d minus e1, and then we go to O of x of md, and then we quotient. So here we're just doing the sequence for d or for md. So we do the sequence for e1, so the ideal sequence, and then we here, and then we tensor it up to md. So we have this sequence for E1. Okay, and now we'll see that this thing here is actually equal to O of x. So we're going to place one copy of D with this. Okay, so when we replace one copy of D with this, it's going to kill E1, and then we're going to get a minus E2. So we're going to have m minus 1 D minus E2. And so so we have this sequence with the positive part. And now we're going to get the corresponding sequence with the negative part with m minus 1. So this is O of x of m minus 1 d. And then we have here O of e2 m minus 1 d. And then this goes to 0 and this goes to 0. Okay, so this is the positive-negative sequence here. And the idea is that it's going to allow us to relate these two pieces. Okay, so now we're just going to do our Euler characteristic thing where we take the additivity of the Euler characteristic. So we have that the Euler characteristic of O of x of md, okay, from the first sequence is going to be equal to the Euler characteristic of O of x of md minus e1 plus the Euler characteristic of O of e1 of md. So all I did is I took this sequence here, and then I chopped it up. Okay? So I did the Euler characteristics of this, and this, and this. Okay? And now I'm going to do the same thing here. I'm going to stop doing the E1s. Well, let me shorten this notation a little bit. So I'm going to do the exact same thing. So we have x, and then we have m minus 1d plus is equal to the Euler characteristic of the outside thing, which was still x. We had m minus 1 d minus e2 plus, and then we had this other Euler characteristic. Now this was on e2, and it was of m minus 1 d, the restriction. Okay, so we have this. Okay, so the other thing that we had was that these two terms, this one here and this one, were equal. This was because d could be written as the difference of or the sum of a positive and negative divisor. So now let's write out the equations. Or sorry, we already wrote out the equations. Here are the equations. And so we can kind of now set these equal to each other. So we have this of x of md, okay, minus this one, e1 of md, is equal to here of now we have this. So this was equal to this here. Okay, and now this thing is equal to this. Okay, which is equal to the difference of those two, and that's what I'm writing down. M minus 1 d minus here of E2 m minus 1 d. Okay, great. Okay, so now what we can do is we can look at the difference of these two things. So there's an important fact. This tells us that here x of md minus of x of m minus 1d is equal to here of e1 of md plus, or let's see, minus of e2 m minus 1d. Okay, so now we can apply the induction on dimension. So this is where the induction on dimension works. So here, notice that these guys have dimension, so E1 and E2 have dimension less than x, x. Okay, and there's a fact that so these two things are numerical polynomials. So this implies that so chi of E1 of MD and chi of E2 of m minus 1d are numerical polynomials. And the difference of two numerical polynomials is a numerical polynomial. Okay, and similarly, so this tells us that this difference of minus d is a numerical polynomial. Polynomial. Okay, and so maybe I'll do this in another video on numerical polynomials, but it would be you know, a waste, like kind of a distraction to do it right now. But the difference of two numerical polynomials, or sorry, if the difference of two things is a numerical polynomial, this tells us that this itself is a numerical polynomial, is equal to a numerical polynomial. Okay, so when you have the difference of two things being a numerical polynomial, then you have a numerical polynomial. Okay, so this tells us that this thing is so by induction, we can conclude that this is actually going to be a polynomial. And that's the Hilbert polynomial, so that's in one dimension. To get the higher dimensional version, okay, so now I think I actually know three proofs of the Hilbert polynomial. There's okay, let me just state them since I brought it up. There's the proof from Riemann-Roch. There's this proof that I just gave from splicing, and then there's another proof associated where you can just take a graded ring and then look at the dimensions of the graded rings, and then this is the fact that if you have a finitely generated graded ring, then this is going to be this is going to give you a polynomial as well. So it's three different proofs. So what do we want to say now? Okay, so we can conclude. So that proves So let me stop the video for a second and get more paper.